All right, so let's see what we can do with this proof. So our theorem is if we have k over f of field extension, A is an algebraic element of k, and p of x is a non-zero polynomial of least degree in this set of all polynomials that A is a root for, then that polynomial, that of minimal degree, is irreducible, and it divides everything in that set of all the polynomials that A is a root for. All right, so let's see what we can do for our proof. So we're going to be supposing that k over f is a field extension, that A in k is algebraic over f, and that p of x is of least degree in IFA. So that means p of A is 0. It means A is a root of the polynomial p of x, and the degree of p is somehow minimal in this set of all polynomials that A is a root for. All right, so we're going to try first to show that p is irreducible. So we're going to say, suppose p of x is equal to g of x times h of x, where neither g nor h of x is degree 0. Okay, so in other words, what I'm supposing is that p can be reduced, i.e. suppose p of x is reducible. Okay, so I'm doing a proof by contradiction here. I'm going to try to contradict something. Okay, and what I'm going to contradict is pretty quick. We're going to say then p of A is just g of A times h of A. So 0 is g of A times h of A. So either g of A is 0 or h of A is 0. And so this means that A is a root of either g of x or h of x, which are both polynomials of lesser degree than p of x, contradicting the minimality of p's degree. Okay, so there's our contradiction. If we could reduce it, then what we would actually have is another polynomial that A is a root for, and that can't happen because p was supposed to have minimal degree. So that's part 1 of our theorem. Part 2 was supposed to show that p of x divides everything. So now to show p of x divides every element in IFA, we're going to suppose, let's say, f of x is in IFA. So f of A is 0. We're going to use the division algorithm to write f of x as some q of x times r of x plus a remainder polynomial. Okay, and that remainder polynomial is either 0 or the degree of it is less than the degree of p of x. And clearly we want to prove is that r of x is 0. We want to show that f of x is just a multiple of p. And you might see, again, what we're going to run into is that idea that the degree of r is supposed to be less than the degree of p, but p had a minimal degree, right? So let's see if we can unravel that argument. All right, so now, just like before, we're going to plug in A. So f of A is equal to q of A times p of A plus R of A, but f of A was 0. I don't know what Q of A is. That's fine. I can leave it there because P of A is also 0. And then I have R of A. I don't know what that is either. But if we look at that equation, it means R of A is 0. And if we look at the above, since we can't have a non-zero polynomial, which A is a root for, that's of lesser degree than P, that must mean that R of x is actually 0 for every x. So I didn't put that in the greatest way. Let me see if I can argue it again. So R of A has to be 0. That either means that R is the 0 polynomial, or it means A is a root of R. If A is a root of R, then R should be in that ideal IFA. But R's degree is less than P. And so that's not allowed because P had the smallest degree in that set. So this is our proof of this theorem. And so therefore, P of x divides every element in this ideal, which is something we sort of suspected based on our example.